Hey everybody, and welcome back to Linear Algebra Online. So the plan for today is to really talk about some formalism behind the idea of a linear transformation as like a function, basically. But I want to start off and kind of talk about some like geometric matrices that I want you to kind of be able to visualize. So in the 2x2 rotation thing, I talked a lot about how you can interpret like a matrix as just like where the basis vectors, like the standard orthogonal ones that you're used to, like I hat, j hat, k hat, that kind of stuff, where they land. And so you can use that to kind of visualize what different matrices sort of do. So in this one, right, it's basically saying I hat doesn't move, right? But instead of 0, 1 for j hat, right, you're doing 0, -1. And if you kind of draw a picture and think about that, so I hat is here, but this vector, I guess I'll do it in red, right, is flipping to 0, -1. And so this is really, this is negative j hat. And so you can kind of see that what that matrix would do is, generally speaking, it's going to act as a flip across the x-axis. Anything on the x-axis would stay put, but anything else is just going to flip over, okay? Kind of similar here. So now you've got j hat going to j hat, so that's not moving, right? But here you've got I hat going to negative I hat. And so in this case, right, you've got this kind of vector staying put. Nope, sorry, not at all. That's the one that moves. It goes over here. And then this one stays put, right? And so in this problem, you have that basically it's a flip over the y-axis, okay? Here, if you sort of flip the two, so I hat is going to j hat, and j hat is going to I hat, right? In this case, then you basically, if this one moves over here, and then that one moves over there, right? You can see there's like a line of symmetry that you're sort of flipping over, and that matrix truly is a flip over the line y equals x. This last one, you can kind of interpret it, I guess, two ways. So it can either be, so this is negative I hat, right? And this is negative j hat. And so if you think in terms of where vectors land, right? This vector is landing over here. And this vector, right, is flipping and going over here. And that kind of thing where you flip like that can either be understood as basically a rotation, right? You could be rotating it 180 degrees, I guess either way, actually. Or you can think of it as a flip over the origin. So both of these are correct, and that one you can kind of think of either way. So you definitely want to get in the habit of thinking about matrices in this way. Like, not always is it easy. If I just like randomly wrote down like 1 - pi e to the 7th, and then 1, 1, 1, 1, 2, my brain has no idea what that does. So, some matrices like this one, this trick doesn't help us, but actually in the world there's quite a few problems that you really just need to know, like basic stuff like this. My cousin actually works in some computer graphics engine design work, and I've seen some of the back end, and he has tons of these simple matrices because there's so much just like flip this image or this like texture and rotate this texture and that kind of stuff. So I actually see a lot of these basic 0 and 1 and -1 kind of matrices. So they're important to know. All right. So another important thing to be able to do is to construct matrices that do certain things, right? So here I've got the idea of constructing two matrices where the first one would project a point onto the x-axis and the second one would project a point onto the y-axis. And you should be stopping the video and thinking about these things when they're posed, but I'm just going to jump into it right now. But for the x-axis one, right, we basically don't want to change, things on the x-axis because we're projecting onto the x-axis, but the things on there aren't going to move, right? So I hat will basically go to I hat, but then things that have a y component, like things like j hat, are going to get smushed down to 0, right? And that would actually do it. If you multiply a random, this by a random vector 3, 2, or whatever, you would actually see that this thing projects 3, 2 down to the x-axis. So I'm going to kind of get rid of that. And then likewise, for the y-axis, if you use that same idea, we want to project, things from the x-axis over to the y-axis, and then we want things on the y-axis to stay put. So that would be the matrix that would do that. And these kind of matrices are classic examples of things that are not invertible. And I think the picture that kind of makes some sense. Say we're doing the projection onto the y-axis thing. You could have, vector here, a vector here, a vector here, all these things. And you're smushing, this one gets pushed over here. I'm going to erase that. And then, so I guess I'll do it like this. That one moves over there, right? And then this one gets sent here, right? And this one gets sent here, right? And since you're losing dimension, the idea of that loss in dimension is where you get basically the fact that, really formally, I guess it's the determinant of that matrix is equal to 0, and hence you get that A inverse, or I don't know why I switched to A all of a sudden, but that M inverse is just not a thing. All right. So, just another one of these kind of geometric interpretations of a matrix sort of thing. So, I want to find, this is actually a formal term, this idea of a standard matrix. So, basically find a matrix. It's a sort of a formula for a matrix that does the composition of a clockwise rotation through 45, followed by a projection onto the y-axis, followed by a clockwise rotation through 45 again. All right. So for the clockwise ones, if you go back to so let me just put all these down here. So, and we can even fill in, we just did, so projection onto the y-axis, we just talked about that, that's 0, 0, 0, 1, right? And then for the clockwise rotation specifically, that's the one where there's a negative here, and then the other one, counterclockwise, which is kind of the standard rotation direction in math, is the negative in the top right corner. And the general rotation matrix is just all sines and cosines, right? With one being negative. And so sine or cosine of 45 is the same thing. It's 1 over root 2. So now you can just pop in 1 over root 2 for all of these. And this is literally like how a lot of people do this stuff, like tons of this in like computer generated effects and stuff. Like we want to maybe do some sort of weird thing like this. And then, you can basically just like multiply these two, and then you can multiply that result by this. But if you do all that out, you would basically get the matrix negative 1 over root 2, negative 1 over root 2, 1 over root 2, and 1 over root 2. And so this is what we call the standard matrix that does all these things. And the way you do it is you want to look at it from here over, right? This is the, first thing, this is the second thing, and this is the third thing. But basically, as you do this transformation, it does the rotation, then you multiply by that one, it does the projection, and then it does another rotation. But you can multiply them, so you can just get it all done in one, is the idea. All right. So another famous matrix that your book actually introduces, and I kind of want to explain it here, is this one. So you have a line L. It's just some arbitrary line through the origin in R2. And we're going to find the matrix which represents the transformation which projects some arbitrary vector onto L. Okay, so it's different than, the projection onto X and Y. Basically, we're saying you have, line L could just be like this or something. And it could be defined by, direction vector 1 or 2, N2, I should say. And what we're going to be doing is crafting a matrix that no matter what vector we have, it smushes it down onto that line. If you had a vector on the line, it'll just stay put. But like this one, if that's perpendicular, then it just goes to the 0 vector. That's basically, we're going to need projections, like from Calc 3. And so we're basically just doing, the projection of, either I hat or J hat onto L, okay? And I guess the reason I should explain this a little bit. So I'm going to need a little more room. So, here, this is where I hat lands, and this is where J hat lands. And so, since everything is just built on a projection, we need to, take a thing like I hat over here as just like something for the X component, right? This, column vector right here. And if we just complete this kind of general projection, then that would give us a vector that we could pop in here, which represents the projection onto L, right? I also don't know why I switched to that kind of L. I want this kind of L. So we're going to do L dot I. This is just the projection formula. So this times L, and this is what will go in the first column, because this is where, this is what we're doing with the I hat kind of, the X component is we're projecting it onto L. So L dotted with I is basically just going to be D1, right? And then L dotted with L would just be D1 squared plus D2 squared. And then you're multiplying that times D1, D2. And so we're getting the vector D1 squared over D1, D2. Oops, not D1. I can fix it. D1 squared plus D2 squared. And then D1, D2 over D1 squared plus D2 squared. So that is just literally, the first kind of column here. So we'll put in D1 squared over D1 squared plus D2 squared. and then d1, d2 over d1 squared plus d2 squared. And then, for this one, this is basically just the projection of j hat, right, onto L. And it's the same computation, so I'm not going to kind of go through it, but you would get d1, d2 over d1 squared plus d2 squared. And then you would get d2 squared over d1 squared plus d2 squared. And that's it. So this is a very powerful matrix if you think about it, because now you have arbitrary line in space. And, you could even do L as like 1, 0. So like the one, the projecting onto the x-axis. And if you go through it with 1, 0, I guarantee you will get this matrix right here. I'm not going to go through it for the sake of time, but this is a very powerful matrix, and one that I do want you guys to know. So it's you can honestly take out a 1 over d1 squared plus d2 squared too if you want, and then just remember the tops like that. But this is an arbitrary projection kind of matrix. All right, so the main thing, all that's really important, but really the big thing I want to talk about today is formalizing a little bit about what it means to do like a linear transformation. So you have a matrix and a vector here, and I could ask what is the image of V under A, right? And if you just do A times V, you would get 1, 3, -1. Okay, basically that's just where this matrix moves this vector to, all right? And the domain of this transformation what we plugged in here. This is a two-dimensional vector, and we're mapping it into 3D, which is kind of weird, right? The domain of this would be really just R2. Any kind of vector in R2 would work, right? You could, because this is a 3 by 2, you just need a 2 by really whatever, but I'll just say 2 by 2 for right now. But since it starts off with 2 rows, right? I wanted it to just be a vector. So I wanted it to be a 2 by 1. There we go. So, any arbitrary 2 by 1 vector is like an R2 thing, right? So its domain is R2. And for the range, right, if you kind of build off of that arbitrary vector idea, right, you can take 1, 2, 3, 0, -1, 4, and you can multiply it by some arbitrary vector like this, and you would get that. And if you think about what this is, we're kind of used to putting like parameters here, which you can do if you want, but really...
Mr. Reitmeyer?
So another thing you should kind of notice is like this vector would basically, this is a 3D vector which lives in this plane down here, okay? But the range in general is like just this plane. That's what the output would be. So just kind of want to go through and formalize a little bit of this stuff that we just talked about. So a lot of times we do use the words domain and range in math wrong. And I can't expect a student in Algebra 2 or something to really know how to use it correctly. But domain is really, a lot of times students just describe the things that get transferred as the domain, which is part of the domain. But the domain is really like the entire space that like the vectors could come from, right? So, in this last problem, they would maybe describe the domain as like just the 1, -1. But the domain is the R2. It's saying that any, this entire space, it's a set, right, that your vectors come from. So that's what domain is. And then this is a word that we don't even bother teaching students in like Algebra 2 and stuff. But there actually is something called the codomain, and we only teach the range in Algebra 2, but the codomain is actually just as important. And the codomain is like the blue space here, which our range lives inside of, okay? So the range is actually formally a subspace of the codomain, right? And the range of a transformation is really the just the column, the column space of that matrix, okay? But yeah, like the f of x that you get in like Algebra 2 and stuff, that a lot of times, well, people is like all you talk about, but you could talk about this bigger space that output lives in, and that's what the codomain is. Right? And just to kind of clear it up with that last problem I did, geometrically, the range space of this transformation would be a plane through the origin in R3. Okay, so the plane is literally just described down here, right? You could take 1, 2, 3, and 0, negative 1, 4 is like direction vectors. That is the range of the transformation, but the codomain is the thing that plane lives in. So the codomain is R3 here. So you can literally, honestly, just do it by rows. And I'm even going to formalize that a little bit more, rows. So this thing had 3 rows, which, so basically m by n, the m is always the codomain, okay? And actually the domain is the n, but that's actually on the next slide that I'm going to show you here. So this. So this is like the formal definition of a linear transformation. So it's a big one in linear algebra. So a linear transformation like T or something takes like u to v, and is a function that carries the elements of a vector space, which you don't know much about, and we will talk about more as the year goes on, u, okay, and this is what we call the domain, to the vector space v, which is what we call the codomain. Whoops, that is not how you spell the word domain. I'm going to squeeze it in, domain. And it has 2 additional properties. And these properties should look pretty familiar. So they should look like a subspace kind of properties. So it's saying that the transformation to be linear means that the transformation on a sum is equal to the transformation of each part individually added together. And that's for all like, U1 and U2 in the domain. All right, this is a U. And then it's saying that the transformation of a scalar on a vector is the scalar times the transformation of a vector. So basically you can pull scalars out. And in terms of a matrix, this has always helped me a lot, just kind of seeing the colors here that I'm going to explain in a second. But say we have like some, matrix, like in that last problem, A was a 3 by 2 matrix, right? It always seemed kind of weird to me, but the columns, okay, are related to the domain, okay, the purple things, U, right? And the rows are the codomain, the V things, okay? So I could give you any matrix. I mean, we could take this. Nope. This thing, sure. And this is a 2 by 2 matrix, which means that you plug in things in R2 and you output things in R2, which makes sense because all we were doing was projections. We're not like all of a sudden jumping up or down in dimensions and stuff like that. Even if we lose a sense of a dimension, we're just projecting to a 2D vector that lives on a 1D line through the origin. So yeah, because this was a 2 by 2, both the domain and the codomain would be R2. And to give you an example of a very famous linear transformation, say we have d dx. This is one of the few times that I'm going to do a derivative this year. So nope, that's not the example I want. I want like d dx of x squared plus 2x. Okay, so we can do this derivative in like that way, right? Or we can, in a sense, sort of distribute that derivative operator to each of these parts. Wow, I am just messing this up. And those are equal, right? This right here is property number 1. It is a very important property of the linearity of a operator. The derivative is a linear transformation. And actually, I can show you eventually the matrix that is a derivative operator. There is literally a matrix that does this. There's also a matrix that does an integral. And I hate to say it, but basically all the ways that you've done derivatives in the past kind of go out the window once you know the matrix, because you sort of just pop things into a computer with that matrix and it does the derivatives for you, or integrals. This is property 1, and then property 2, right? I can just do with like, it's not a partial. I can say like, the derivative of 2x could also be 2 times the derivative of x, and that is property 2, right? Basically, scalars move outside. I can pull scalars outside. That's what it means to be a linear operator. All right. I want to go through this. So just consider this transformation below. And this is actually kind of how we write it. So t of xy equals this. So you can see here it's taking a 2D thing, right? So something, actually I should just do like this. So something in R2, and it's sending it to a vector with 3 components, so something in R3. And the question is this a linear transformation? So we got to go through the 2 different kind of properties. So property 1, we're going to do t of u plus v. So just arbitrary xy vectors. So that's going to be like t of this. And we want that to equal t of u plus t of v. So I'm going to start by adding things together. And now I'm going to go ahead and, put this in for x and this in for y. And now I'm going to go ahead and basically just simplify this thing. And now that I've got this thing grouped kind of with x1 and x2s, you'll see that I can now kind of split the thing like this. And now, if you look at that, that is literally just t of u plus t of v. So this proves like property 1. And sadly, I don't think I have time, but it's actually in the book, so you can read it. But for property 2, you would basically need to do, it's actually much shorter, t of c times like some arbitrary vector again. And, you'd start off and that'd be t of like c times like xy. And you basically just need to go through the same kind of thing where you multiply in, and then you're going to kind of like group some terms, but you need to do ... and then show that you get c times t of xy. So you should read that in the book, but that's basically how you prove that a linear transformation is linear. You just go through the 2 properties, and a lot of times it's just this kind of tedious algebra sort of stuff. And that is the very bare bones of linear transformations. We're going to do a whole nother day with this in the next video.